Good afternoon, everyone. I'm Changyang Gu from ByteDance Presto team. Today, I'm very excited to take you through our exploration of Prestissimo compared with PrestoDB, and particularly focusing on the TPC-DS benchmark and our optimization process. This is today's plan. First, I will go through the Prestissimo and Presto overview, then our key improvements and optimization process. Next, our detailed TPC-DS benchmark results. And last, my colleague Shegnxuan will talk about our future plan and contribution to the community. In the realm of big data, efficient processing is key. At ByteDance, we have been leveraging PrestoDB for its impressive capabilities in handling a vast amount of data. To further enhance this, we take advantage of Prestissimo, a variant that introduces native C++ worker by using velox. This innovation aims to improve the CPU efficiency through the vectorized computations. And this is a crucial need as our company-level data processing need escalates. Yeah, this page I will show our company's PrestoDB usage and configurations. At ByteDance, PrestoDB forms the backbone of our data processing infrastructure. We have around 2 million read-only interactive SQL daily. And for the cluster details, we have 96 cores, 384 gigabytes memory, and 550 gigabytes SSD. This SSD we mainly use for Presto local cache. Our PrestoDB interact with critical data sources like Hive table on HDFS. We also use shared Hive metastore with other engines and databases like Spark, etc. Yeah, as you can see, this extensive usage not only underlines the reliability of PrestoDB, but also set up the stage for our future exploration of Prestissimo. These slides, I will talk about why we choose Prestissimo and what's the advantage of using Prestissimo. Why we choose Prestissimo? The inception of Prestissimo was driven by a clear objective. We want to enhance the CPU efficiency and manage the growing resource demands on Presto. The Prestissimo provides a native C++ worker directly by using velox, and also it improves the CPU efficiency. Prestissimo is designed to embrace the vectorized computations. And most important, Prestissimo saves the overall resource costs with the increasing needs of Presto. This page, I will talk about our TPC-DS benchmark evaluation. At ByteDance, we are using our company Volcano engine as our servers. That is our logo, and we have 8. Each cluster we have 8 Prestissimo workers, and each worker it has 32 core and 128 gigabytes memory. For the testing data side, we have 1 terabyte TPC-DS testing data. We only in packet format, and we store it in the HDFS. Yes, and for the TPC-DS queries benchmark results, we have successfully passes all the 99 TPC-DS queries in the above setups. This is a significant achievement showcasing Prestissimo's compatibility and great performance. Yeah, next part, I will talk about our key optimization and some improvements through our code implement. Today, I will include two main optimization in this talk. First, which is vector hashers optimization. The second, I will talk about our how we optimize semi-hash join from the memory and time complexity side. Yeah, first, let's go to the vector hasher side. This is the background about vector hasher. Vector hasher in Velox right now is designed to hash vectors. It's a process typically utilized in tasks such as data aggregation or deduplications. The vector hasher, right, it will process entire inputs, hashing all values successfully, except in cases where it encounters a value that cannot be hashed. From these pictures, we can see if I have a column called age, vector hasher will hash entire age column values. And in this slide, I will talk about our own optimization steps. Our optimization concept is, instead of analyzing all values, the proposed change is to analyze only the remaining values in the input until all unique values have been encountered. This is particularly effective in the low cardinality, large batch size workloads. Our implementation details is we want to involve modifying the analysis process to stop once all unique values are identified. In this way, we reduce the unnecessary computation. Next, I will show you an example to explain how it works. Consider we have a table of 20 million rows, very big table. One of the columns only contains values between 0 and 120. Our optimizations, it will stop when we encounter all the unique 120 values. After that row, we will not move forward to the next row. In this way, we reduce the total rows of input values and enhance the vector hasher's processing speed and efficiency. Yes, theoretically, for example, if we have a batch size of 1024, this optimization could result in 8.5 speed up in compute value IDs. As you can see in this picture, this is a very big table. When we identify all the unique values, I will stop, and in this way we reduce the time complexity and increase the efficiency. Yeah, in the real-world scenario of analyzing a certain table, this optimization in vector hasher can lead to substantial improvements in processing speed and efficiency. And it is especially beneficial in a large data set with low cardinality in certain columns. Yeah, second optimization we have been done is about how do we optimize the semi-join from the memory and time complexity side. Here is the problem description. Hash build operator in Velox, it will store all the new data into the container called row container. As it comes more rows, this row container will grow larger and larger. So for hash table of semi-join, which we do not need to duplicate case, we should avoid adding too many duplicate rows with duplicate case. Yeah, this is a picture about the problem. As the picture shows, in Prestissimo, this actual hash table is not built until all input data is received. Before then, the raw data input is stored, as I said before, in the row container. And this data object can be significantly larger than the ultimate hash table, especially when no duplicates in the hash table are allowed. In this case, like semi-join. As this picture shows, we have a table and also we have a name column. Right now, Velox will hash every name and then store in the row container directly. Yeah, so the key point is how to avoid adding too many rows to the row container. Here's our solution. Mainly, we adding a efficient LRU cache to make sure this key exists in row container. Otherwise, it will be wrong. Therefore, because of this pre-assumption, we choose this LRU to make sure only the hash key, no duplicates, will be inserted in the row container. And in this slide, I will walk through more details about how we do this. In experiment, like our experiment, the same test data using LRU cache will reduce the size of final row container. Because when LRU cache return key identified, we do not need to add this row into the row container. So for a hash table doesn't allow duplicates, we calculate the hash of the case. If the key exists in the row container cache, which indicates it's already exists before, so we do not insert it. If it doesn't exist in the cache, we might need to insert into the row container. Yeah, so in this picture, we add a cache layer before inserting to the row containers. I just need to check if the hash value, if it's inside this cache or not. If it doesn't start in this cache, what I need to do is I insert it to the row container. And also, in this way, by using this LRU cache, we reduce the total number of rows inside its row container. And also, for the following steps of building the hash tables, because of the reduction of the number of inside this row container, the time of building the hash table will also be reduced. Yeah. This page, I will show you our result comparison about the last optimization idea. We go through the TPC-DS queries. Query 95 is a heavy semi-join cases. So I will use that one as our case. From the results showing, we got some significant achievements. First, the significant peak memory usage is going down by 20x. So because of this memory usage going down, we prevent out-of-memory issues. Secondly, the average memory usage of query 95 goes down by 25%. Thirdly, the end-to-end time of query 95 also reduced by 25%. Yeah, this is a pretty great comparison and for the before and after of this query 95. And that part, and next, I will pass it to my colleague Shengxuan to let him present.
Thank you. Yeah, thank you, Changyang, for this great presentation. My name is Shengxuan. I'm from the Presto team from ByteDance as well. So for my presentation, I will focus more on our TPC-DS results and our future plans. So let's start with the TPC-DS results. So firstly, I would like to make a small disclaimer about our testing background. So firstly, we are comparing with ourselves. So it means that we are comparing our internal PrestoDB with the new Prestissimo on these identical clusters. Secondly, we are using the same Presto coordinator. So it means that the logical plans are the same for both Presto and Prestissimo. And also, we're using 1 terabyte of Parquet data. And they are Hive tables, and they are on HDFS. And lastly, there's no cache enabled. We do have a Presto local cache enabled in our production environment, but for this TPC-DS test, we're not using cache. So let's go to the results. The results can be divided into 2 parts, the coverage and the performance. So for the TPC-DS coverage, we started the Prestissimo project more than 1 year ago, and at that time, only 76 queries were able to be passed. And now, after more than 1 year of the joint effort of both the great communities and our Presto team, we are very proud to say that all the 99 TPC-DS queries are able to be passed. And during this year, a lot of important features have been added to Prestissimo and Velox. And as Changyang just presented, our team have also contributed a lot to the performance and bug fixing of the Prestissimo. And in the meanwhile of rolling out of the Prestissimo against the TPC-DS test, we have identified several critical bugs. And for example, I work on the Parquet readers, and I have fixed several bugs on the Parquet readers, and now the Parquet readers are pretty stable. So with all these efforts, we are able to pass all the 99 TPC-DS queries. And now let's talk about the performance. So for the performance, as I said before, we're comparing the Prestissimo against PrestoDB. And we have observed a 1.67x performance improvement on the total end-to-end TPC-DS executions. So that means that the total end-to-end time cost of the TPC-DS executions have been reduced by 40%. And on the other hand, we have also observed 57% of the average CPU saving. So it means that the Prestissimo is able to save more resource. So here is the very detailed TPC-DS results. As you can see, I have put all the performance improvements or reductions and in this chart. And overall, the results are pretty good. And you can see that a lot of queries are able to be even 5x more faster. And however, we can still see that about 20% of these queries are not good enough. You can see in the top of this diagram. So based on this, we have made a lot of analysis. And so and these will also be our future works. So we have identified several works that we still need to work on. And so firstly, we plan to optimize the hash join for lower peak memory usage. So for Velox, Velox built the hashables from the root container all at once. So it means that the vlogs will collect a lot of data before actually build this hashable for better hash mode selections. And our analysis shows that we can probably implement a sampling algorithm for this part to reduce the peak memory usages. And secondly, shuffle compression. Shuffling is very important for the distributed data engines. And so we're planning to implement the compression for the shuffle data. And we can use ZSTD or LZ4 or other pretty efficient compression algorithms. In this case, we're able to reduce the total size of the shuffle data and improve the overall shuffle efficiency. And lastly, for Parquet Reader, so we plan to push down the filters to the decoding part of the Parquet Reader. So currently, the Parquet Reader does not support filter push down to the decoding layer. So even though, so for the data that have been filtered out, these data still need to be materialized. And with this optimization, we're able to avoid some unnecessary materialization of the filter out data. And that's all our future works about our Prestissimo project. And thank you so much for your attention. And thanks again, everyone.